Ladies and gentlemen, dear colleagues, welcome. I am Zdeněk Hanzálek, and I thank you for watching the 22nd installment of the scheduling seminar. The seminar has 1 year anniversary, so let me show some statistics first. So up to now we had 21 talks, and in total there were like more than 13,000 views from YouTube and Zoom. So in average it gives like more than 600 views per talk, and we have 600 subscribers on YouTube that are notified when there is a talk. So we have, if we look how many people are watching per month, then we have monthly record on YouTube more than 1,000, out of which there are 600 unique viewers. It means like independent people watching at least one talk. So most popular talks, if we look open them by season, so in spring last year was the most popular was the first talk given by Jan Karel Enstra and David Mois. In fall it was the talk given by Benjamin Mosley, and in winter up to now there is Dvir Shaptai's talk. So you see, I think all of the presenters here, as you see, we are very nice and good looking people, more than we expected. So it's I'm pretty sure that the future in front of us is marvelous. So, and then how are the statistics? So if we look open Zoom statistics, so Zoom is used just online, so it doesn't grow up during lifetime, but you can see here like all participants statistics joining one and every talk, and also number of participants that are concurrently watching the talk. Okay, so we can see that in average we have like between 100 and 200 participants watching on Zoom, and at one moment there is something like maybe 80 people in average watching the Zoom. This is the peak number, so if they are just starting at the beginning and then they disconnect, that's not visible here, right? On YouTube we have let's say like around 200, 300, 400 views in average per talk, these blue columns, and there is much less people watching online, which is given by this red curve. There might be maybe like 30, 25 people in average watching online. If we look open YouTube statistics per month, then we can see that except of summer holidays, we have like from 700 up to 1,000 views per month. It means accumulating views on all different talks. Okay, so that's about statistics. And now let me come back to topics of today's talk. So let me introduce Christian Artigues. Christian is interested in operations research, combinatorial optimization, and constraints. It's also the name of his group at LAAS CNRS Toulouse. In 1997, he did his PhD degree there. And then he was in different positions in Besançon, Lille, Avignon. And in 2005, he was invited researcher in Center of Transportation Research in Montreal, Quebec. And since 2006, he is back in LAAS CNRS Toulouse, heading this so-called ROC team. So they are hard guys, right? He was very active, as far as I know, in RODEF Euro challenges, and then that's it. So Christian, welcome. It's great to have you here. And the floor is yours. So please share your screen with us.
Okay, I think you should see my screen.
Yes, it's visible. Thank you very much.
Thank you, Zdenek, for the nice introduction, and thank you also, Mike, for organizing this nice series of seminar, and also thanks to Rainer who proposed my name for this talk. So I will talk about mixed-integer linear programming approaches for resource constraint scheduling. So the outline of my talk is the following. So I will mostly talk about a project scheduling problem, which can be seen as a particular case of the resource constraint scaling problem with precedence constraints. It is one of the most basic problems in this area, and we will also talk on different variants of this problem, not necessarily related to project management. So that's why in the title I removed the project word. And I will try to make a survey of mixed-integer linear programming techniques to solve this problem, and to try to give a few hints on why and when using Milp for scheduling problems in practice. So first, about the Rcpsp, the resource constraint project scaling problem. So it is a stack scaling problem with standard finish start precedence constraints, and also resources of limited availability that make this problem hard to solve. We have to find the start times of the set of tasks while satisfying the precedence and resource constraints. So the objective is to minimize the makespan, which is the total duration of the projects, but there are also several objectives. I will discuss a bit about them. So it's a computationally challenging and paired combinatorial optimization problem, as it generalizes many standard scaling problems that were already discussed in this series of seminars, like one machine problems and parallel machine problem, job shop, assembly line balancing problem. The Rcpsp was also presented last month by Eric de Meulemester in his talk about uncertainty management. Rcpsp is also at the core of many industrial applications, as we will see. So it's a problem of interest both in theory and practice. So I will first define the problem formally. So we have a set R of resources. Each resource has a limited constant over time availability, BK. Okay, and we have to schedule a set of activities. Each activity has a duration, PI, and also on each resource a requirement, BIK, that can be 0 or of course lower than BK. And we have in the Rcpsp basic problem a set of finish start precedence constraints, IJ, gathered in the set A, and we have a time horizon on which we have to schedule all activities. So here we see a project with 10 activities, and you see the precedence constraints, and on the right side you see the duration PI of each activity, and also we have a single resource here, and you see the requirement of each activity on the resource, knowing that the availability of the resource is B equal to 4. Okay, we have 4 units available for this resource, so you see that all activities asks for less than 4 units, and we have to schedule the project under a time horizon of 13 time units. So this is how do we model, well, let's say conceptual formulation of the problem. The decision variables are the start times. You can define them as continuous positive variables. And you have also the special variable, which is the makespan, Cmax, that you want to minimize. And the makespan is equal to the maximum over all activities of the start time plus the duration of the activity. You have precedence constraints that states that the start time of an activity J cannot be lower than the end time of the preceding activity I, Si plus Pi. Okay, and the second set of constraints are the resource constraints. So these constraints here use the set A of T, which gives the set of activities. You have the definition on the bottom of the slide. The set of activities that are in process at time T. It means that T belongs to the interval made of the start of the activity and the end of the activity. So for all these activities that are in process during time T, you can sum up the the requirements, and it cannot exceed the resource availability. So this is the resource constraints. So of course, this is not directly, let's say, you cannot give this to a solver because set A of t depends on the decision variables. So here you see below a Gantt chart of a solution of these 10 activity problems. You see that we have a make span of 24. You can see that the constraints are satisfied. For example, activity 4 does not start before the end of activity 1 because we have here a precedence constraint. And you see that the capacity, the availability of 4 units is never exceeded. So you see, for example, that here 7 and 8 can be scheduled in parallel. But we cannot add another activity in parallel because we already reached the capacity limit. Okay, so this is a problem we want to solve. It's a central problem, as I said, in many applications: project management, manufacturing, process industry, and also inside the computer architecture, like parallel processor architecture. You have to solve this kind of scheduling problems. So about the standard Rcpsp, it's an NP-hard problem that is posing a computational challenge since the 80s, and we can find in the literature and also available on internet a lot of benchmark instances. You see here a series of papers that propose new instances for the problem. Most famous library is the PSP-lib by College, Sprecher, and Drexel. I will also talk a bit about the PAC instance set from Carrier-Néron, and recently there were new instances proposed by Coelho and Vanouk. To give you an idea about the difficulty of the Rcpsp, you still have 24 open instances with 60 activities on the PSP-lib set. And you have 60 activities and 4 resources, and the optimal make span is still unknown for these activities. So about the Coelho and Vanouk, they recently created rather recently created a website where you can find all the best known solutions for all the instance sets that are reported in the literature. For example, here for the PSP-lib, you see that the 60 activity instances, you see these 24 open instances, and you see here which methods progressively close the benchmark set. For example, here the 30 activity set was closed by the Demeulemeester and Herolen branch and bound algorithm in the 90s. So you can play with this, of course, for your own research. It's a very nice site. So as I said, the problem is a strongly NP-hard. In general, is many scheduling problems. We have in practice to consider many relevant variants. For example, the objective function, we can have a weighted sum of completion times of other objectives. We can have generalized precedence constraints, where in fact the predecessor is not only linked to the successor by its duration, but it can be any positive or negative value. And when you have negative value, it corresponds to maximal time lags that make the problem difficult, even more difficult to solve. Also, you can have setup times on the resources, multiple modes for the activities, when the activities can have several ways of being processed, which makes vary both their processing time and their use resources, non-renewable resources, and preemption, when you can interrupt the activities. And also, you can have uncertainty of the problem that is totally out of the scope of this talk. So as let's say, all famous combinatorial optimization problems, the Rcpsp has been attacked by all kinds of methods, from heuristics and meta-heuristics to dedicated branch and bound methods, specific lower bounding approaches, and more generic approaches like constraint programming or hybrid SAT constraint programming approaches. And this talk focus on mid-interval linear programming. And also on large number search, which is a local search approach where you can solve a sub-problem with exact methods such as Milp. So I will talk about this later. So I will give you an example of a few applications, and some of them So I will focus only on exact methods, so and more precisely on mixed integer linear programming methods, but I will often compare with CP approaches which are up to date the best methods to solve exactly this problem. So sometimes Milp can do better, we will see in which cases. So I will give you a few applications now on which I worked with some co-authors. So, for example, we did a work with Gilles Simonin, Pierre Lopez, and Emmanuel Ebrard on the scheduling of the experiments of the Philae lander on the comet. And it was a Rcpsp, and the activities were the experiments performed by the lander. The resources were converters in a hierarchical way. So for a single experiment, you can use several converters of limited power capacities, and we have special data transfer constraints. But this problem was solved by CP. Okay. We did another work here with Tamara Borreguero, also Pierre Lopez and Tom Portolo and co-authors on the assembly line scheduling for the Airbus A330 airline. So it's a Rcpsp also with a bit less than 1,000 activities. Resource are operator groups that have to work on the assembly line. And we have a fixed make span to satisfy of 14 to 25 days. And the objective is to minimize the peak of each operator group used. And so for this problem, Milp did not work at all. So we had to solve the problems through CP and large neighbor search. Another problem on which we worked recently with Oliver Polo, Pierre Lopez, and Lars Munch is a problem of scheduling hazardous material examinations. Here, the resources are of two types. You have special resources to store the hazardous material, and you have teams of operators with a high regulations rule that form the resources of the problem. And they have multi-skill, each employee has multi-skills, which make a variant of the Rcpsp also. But here we have about 100 activities to schedule in a week. And so, as you see, this problem can be solved by Milp, and I will explain you why later. And the last problem we will discuss a bit in this talk is the work that we made with Maximilian Paul and Rainer Kolisch on the scheduling integrating runway snow removals and aircraft operation scheduling. So we have to schedule landing and takeoff of planes on runways. But at some point, we have also to schedule a snow removal, and a snow removal operation, of course, uses a runway, but also a group of vehicles. So it's a kind of parallel machine problem with setup times, precedence constraints, multi-resource requirements. So what is interesting here is that the cost is a sum of convex earliness tardiness costs. And for this problem also, we experienced that hybrid approach using CPL Milp was really interesting. I will come back at the end of the talk on this. So for all this application, the core problem is the Rcpsp. So before going to Milp, before giving a Rcpsp to a Milp solver, we have to do some pre-processing. The pre-processing is mainly in the literature is to introduce time windows for the activity. So first you compute an upper bound with a heuristic. For example, you remember we have a heuristic that could have given us the schedule of the make span 24. And now we have to compute a lower bound for the starting time of each activity. So you have the famous critical path lower bound, which I'm computing the longest path in the precedence graph. So here we have 16. And we have also a trivial resource bound. So we on each resource, we take the sum of all resource requirement time the duration, and we divide by the capacity of the resource. And we take the max of this over all resources. So we obtain a better bound of 16.5, which means 17. So by basic longest path computations and taking account of the heuristically found make span, we can compute these time windows here, the first time windows for the activities. And we can also use a more sophisticated and dedicated constraint propagation technique using resource requirement to reduce this time window. So here you have at the right hand side time window reduced by constraint propagation. So I think that the next talk is by Pascal Van and Henrik. We will talk about these techniques to obtain such reductions. So it's really important for Milp to do this pre-processing before we see that why after. So now, what is the basic principle of using Milp for scheduling? So it's linked to the scheduling polyhedron. So in fact, for any scheduling problem, say with a linear objective function and continuous start time, you can define two sets. So I take a simple example here with two activities, one resource of capacity 1, means a machine. You have two tasks with duration 3 and 2, and then you have release dates and due dates as we just computed with our pre-processing, for example. So one task has a release date of 0, second one of 1, one task has a deadline of 9, and the second has a deadline of 7. And the objective function here, to simplify, is the sum of the completion times. So the problem can be formulated as follows. So we have to satisfy the time windows, and we have as we have on one machine actually a resource of capacity 1. Either we schedule task 2 after task 1 or task 1 after task 2. And as we have two variables, we can draw the feasible solution in the plane. So in the dotted black rectangles are the feasible start time solutions. As you see, it's a union of polyhedron. So it depends on if you decide to schedule 2 before 1, you have 1 polyhedron because everything becomes linear. If you decide to schedule 1 after 2, you have another polyhedron, and it's also linear. So it's a non-convex set. So that's why the problem is difficult. But if we manage to draw the red polyhedron, which is actually the convex hull of the set S, then we have only to apply the simplex methods to find the optimal solution, because you can use the simplex algorithm or interior point, polynomial interior point algorithm to find the optimal solution in a polyhedron. So for any scheduling problem with this linear objective function, in theory, you can find this polyhedron, which is a convex hull of the feasible solutions, and then you apply the simplex method on it. So that's the main principle of Milp for scheduling. Okay. The problem is that in practice, for most cases, we cannot. It's NPR, of course, to obtain this polyhedron. It's almost impossible in practice. But everything is linked to this principle when you are using Milp for combinatorial problems and especially scheduling problems. So more formally, we have to define a mixed integer linear program for solving the scheduling problem. So we suppose that we have the start time vector as decision variables and an objective CS, okay, and calligraph LS is the set of feasible solutions, okay, the feasible set of the Rcpsp. And now we suppose that we have to introduce a set X of additional P binary variables, and we define a Milp which aims at minimizing for the variables S and X this following linear program. So with the objective CS, a matrix M for the start time vector, and a matrix N for the X variables vector, lower than Q, and S can be a continuous variable as a natural start time variable, and X is a binary vector. So if this is a correct formulation for the Rcpsp, then if we project the solutions on the variable S, then we obtain the set S. Okay, the set of solution is a projection of the solution of this mixed integer linear program on the variables X. So you can search S by branch and bound. So usually we do a tree search on X. And at each node, we solve the LP relaxation, which is in red here. We say that X now is in the interval 0, 1 instead of the binary values 0 and 1. And at each node, once we have defined the linear relaxation, we solve it with some LP algorithm like the simplex, and we obtain a lower bound, and we use this lower bound to cut the search tree with other upper bounds than we can have found. And we will try to get closer to the convex hull that I presented before by incorporated at each node also valid inequality, which gives the branch and cut algorithm, which is implemented in the commercial solvers like Cplex or Gurobi and others. And the lower bound will be tight if it's close in some way to the convex hull of the feasible set. So here, for example, for our two activity simple example, we introduce these constraints with X variables to which are called big M constraint, because if X is equal to 1, then the first constraint will be cancelled, and if X while the second constraint will be tight. Okay, so with this big M constraint, we can decide whether we schedule 1 before 2 or 2 before 1. And so actually the projection of the Milp feasible set is exactly mapped the feasible set that is displayed now. But now if we relax the integrity of X, in fact, we obtain the feasible set in red, which in fact is only the bounds of the variables. So the constraints are completely useless. In fact, the fact is the 0.5 solution is always feasible. Donc, this Milp formulation does not have a tight bound. Okay, the bound is really bad here. We have the lower bound of 6, which is only the minimum value of the variables in their interval. So we have to branch and bound, or we have to branch. So we take, for example, x equal 1, and we obtain an objective of 9, and we branch on the other variable, and we find the optimal solutions. So that was an introduction, a quick introduction of branch and cut techniques. I'm sorry to be maybe fast, but I have to present the Rcpsp formulation after that. But we have a trade-off to find. So as we see, the previous formulation was really bad, but it was compact in the sense that we have a polynomial number of variables. In fact, here we have only one binary variable for each possible disjunction of the problem. So generally, polynomial size formulation provide a fast node evaluation. You can explore more node, but sometimes the relaxation, like we see is poor. So we have to add valid inequalities and branch and cut. And we will see other kind of formulation in which we introduce more variables or constraints or constraints. And so we obtain a pseudo polynomial or extended formulation. So we will have better relaxation. So we can do early node pruning in the search tree, but the counterpart is that it will take us more time to solve the relaxation because it increases the Milp size, and the size can be even exponential. So we have to resort to branch and price techniques. I will say a few words after that. So when you design a Milp formulation for a scheduling problem, you have to find this trade-off between a compact formulation, but that can have poor LP relaxation, but can be solved fast in the search tree, or pseudo polynomial or extended formulation that have better relaxation, but that will slow the search. So it's a trade-off between inference and search, as in any branch and bound algorithm. So, okay, you could ask me the question, why are you talking about Milp for Rcpsp? Because we all know that the best methods are hybrid CP-SAT techniques. So why using Milp? So in fact, it's not constant over time. Milp solvers are doing more and more progress. So that's the first reason. And in some identified case, you can prefer Milp than CP. If you want, for example, to compute lower bounds, and sometimes for special constraints and objectives also, as I will see. And also Milp can be integrated in hybrid methods like large memory search. So let's go on the Milp formulation for the problem. So these formulations are based on let's say, a pioneering work by Keran and Schulz in '94, and they classified the scheduling Milp according to the type of the decision variables. and each type of decision variable yield a different family of valid inequalities. So there are three families. Either you use the time-indexed binary variables, so the binary variables are indexed by the activity and the time period, so you have to discretize the time period. And the two other, you can use continuous time variables. One is a linear ordering variable, and for the Rcpsp, we either call that a strict order or sequencing variable that state binary variable that state the relative sequencing of two activities. And the last one is originally named in the Keranel-Schulz paper positional dates and assignment variables that we transform into event-based formulation for the Rcpsp. So I will describe now these three formulations and give a bit their advantages and their drawbacks. So first, if you discretize time for the make span objective and the standard Rcpsp, you do not lose any solution, because if all the data is integer, then the optimal solution will be integer also. So we can restrict to the set of integer solutions. So discretization does not harm. And the first family of time index variable is called the pulse variable. It's a variable that is equal to 1 if the start time is exactly equal to the time t. So xit is equal to 1 if the activity starts at time t. So for example, in the solution, we have here, you see that the start time of 1 is 0, the start time of 2 is it's 3, etc. So the binary variable is equal to 0 everywhere except at the start time of the activity. So obviously you don't have a polynomial number of variable because it depends on the time horizon, which could be equal, for example, to 2 to the power of the number of tasks. So it could be, that's why you say it's a pseudo polynomial. So with this variable, it's really easy to write all the constraints. First, you remark that the start time is equal to the sum over the time horizon of t xit, because the xit equal to 1 will give you the start time, okay? So for the precedence constraints, that are the first constraints, you just write them directly with this correspondence. And also you can notice that it's also really easy to express the famous set A of t, the set of activities in process at time t. You just have to be sure that for the activity to be in process at time t, then it has to start at a time tau that is inside the interval t minus pi plus 1 and t. So you have to sum up all the variables xi tau that correspond to this interval, and then you sum their resource requirements, and you say that it does not exceed the capacity. And of course, you have to select a single start time. So it's a model that goes back from the 60s. Let's see in our example of two activities, you will see it has a better relaxation. So if you write the model here, I don't go into the detail. The relaxed feasible set is exactly the convex early in our case. So it's really good, right? So you see, it's really better than the previous relaxation in this simple case. So it's a tight bound. But we need 11 variables for a 2-task example. So you see the pseudo polynomial size of the Milp that appear here. And it's not so good in general. Let's take the 10 activity example, and below I compute in some way the relaxation by if you solve the relax problem, you will have a rational value for the xit. And so, for example, if xit is equal to 0.2, then you assume that you use only this portion of the task here, and then you schedule another portion of the task here and here. So the tasks are spread all over the horizon. So you see that it's far from a feasible solution, and it gives you a bound of not better than the trivial resource bound. Okay, so it's not so good. So to improve the bound, what we can do, it has been done in 97. We can define disaggregated precedence constraints. So to understand these constraints, you just have to think of the logical relation. If the start time is lower than t, the start time of the successor is lower than t, then the start time of the predecessor is lower than t minus pi. Okay, you could just take the precedence constraint like this if you had a logical solver and not a linear solver. But thanks to the binary variable, you can translate this logical expression into binary variable. So here you see that you sum from tau 0 to tau minus pi the start time of I, and then you consider the sum of tau 0 to t of the start time of j, and you prevent, you say that this the sum of x j tau cannot be equal to 1 if it's 1 is equal to 0. So, and what is interesting in terms of linear programming, some characteristic that is desirable when you do a linear program is to have a total unimodularity. So if we consider only these constraints, the matrix is totally unimodular, which means that solving the LP relaxation without the resource constraint, only the precedence constraint, will give you an integer solution. So in the sense, it's a perfect formulation for the precedence constraint polyhedron, okay, not the resource constraints one. But for example, by using Lagrangian relaxation of the resource constraint, the total unimodularity is preserved, and you can have some nice bounds, lower and upper bounds on the Rcpsp by using this. So if we now replace the aggregated precedence constraints by the disaggregated one, now you see the solution. It seems more spread in the time horizon. You have even idle times on the resources, and indeed the bound is better. You obtain 18. So now we can do variations on these formulations. For example, we can define this variable, which is equal to 1. If Si is lower than T, okay, so you see, for example, for activity 3, the variable is equal to 0, but at the start time it starts becoming equal to 1, and it never goes back to 0, right? So it's a step behavior. So is it a really different formulation? As you see in my slide, it has been rediscovered several times, by the way, but no, it's not a really different formulation, because we can switch from the CIT from the XIT formulation by a linear, a non-singular linear transformation. CIT is equal to the sum of 0 to t of the XIT, right? And conversely, XIT is CIT minus CIT minus 1. So this is a non-singular transformation. So the Milp are totally equivalent in terms of linear programming relaxation. They are the same relaxation value. So you can find in the literature some variants, but in fact we can show that they are equivalent to the original value by this non-singular transformation. So another one that can be obtained by another non-singular transformation is the on-off formulation. So mu it is equal to 1 if in fact t belongs to the scheduling interval of the activity. So here, for example, for the first activity, you have a mu I0, 1, and 2 that are all equal to 1, and then they are equal to 0. This has also been introduced and then rediscovered several times in the literature, but we can, in fact, Souza in 98 in his thesis proposed this non-singular transformation that allows to switch from mu to x and to x to mu. It's a bit tricky, but it's linear, and there is nothing that makes the on-off relaxation better than the other ones. So when you design a supposedly new formulation, you have to take care of maybe it's only a linear transformation of an already known formulation. So you need to distinguish this from actual cutting planes or extended formulations. So an extended formulation has a better relaxation, but as a counterpart, you can have an exponential number of constraints and/or variables. And so you will need to use cuts and column generation techniques. For example, on the small example again, we can notice that to minimize the mixspan, the set of earlier schedules is dominant. So it's completely it has no sense in this small problem. But suppose that you enumerate the set of all earlier schedule. You have two earlier schedule, either one is before 2 or 2 is before 1. Okay. And then you define a binary variable for each earliest schedule, and you design a linear program in which you just say that you have to select one of the schedules. So if you take the linear relaxation of this, you obtain this red segment here, and so of course, if you optimize on the red segment, you obtain the optimal solution. So if you would need to enumerate all the earliest schedule, then we will have an exponential number of variables, right? So now we will see how we can obtain extended formulation by several concepts. First, the first important concept is a minimal forbidden set. So what is a forbidden set? It's a set of activities that cannot be scheduled in parallel because they exceed the resource capacity constraint. And a minimal forbidden set is minimal in the sense that if you remove one activities from this set, you can schedule them in parallel. So you have to exceed the capacity, and if you remove any of them, then the capacity is respected. For example, here, 1 and 2 is a minimal forbidden set, 1 and 3 also, and you have also 7, 8, and 9, that is a minimal forbidden set. In general, there is an exponential number of minimal forbidden sets. So if you would to introduce this in a Milp, we would have an extended formulation. Okay, we can have reduction techniques. I don't go into the detail, but this led us to the valid inequality that we can add to a branch and bound to improve the quality of the LP relaxation. So with the XIT variables, we can easily say that the set of activities inside of a minimal forbidden set cannot be scheduled in parallel. Actually, this value here gives us the number of activities that are scheduled in parallel at time t. And so this value has to be lower than the size of the forbidden set -1. We can schedule f -1 activities. So there are too many inequalities to include them on a linear program, of course, so we have to do cut generation. So in the Ardin et al. In 2008 improved this, just to know that there are ongoing works on valid inequalities. They improved this inequality. By the way, it's called the cover inequality because in the knapsack inequality, a constraint such that the sum of the BIK exceeds the capacity is called the cover. Okay, so it's a minimal cover inequality also. So in 2008, Ardin introduced the concept of an interval of length v. That means that if a set of activity I inside a minimal forbidden set is in process during an interval from t to t plus v, then another activity not included in the previous set but inside the minimal forbidden set cannot be scheduled neither. Okay, so it's a stronger inequality. The problem is that how does branch and cut work? At each node, you solve the linear relaxation, and we try to find a violated valid inequality. So if you want to find a violated minimal forbidden set inequality, it's NPR actually. So we use separation heuristics. So you can find in these papers, even really recent papers, new valid inequalities for the Rcpsp and its variants. One technique that is pretty used in all these papers is the lifting technique. If you recall the cover inequality that we just presented, then well, first of all, if you set to 0 the XIT variables of all activities except those in the minimal forbidden set, then this inequality defines a facet of the resulting polyhedron. So, but all the other activities variables are set to 0. So what if we want to include these variables in the constraint, and we try to give the highest coefficient possible to this variable in the constraint? This is called the lifting technique, and it improves the quality of the cut. Another concept used for designing extending formulation is the fusible subset concept, which is a kind of dual of the forbidden set concept, because it is a set of activities that can be scheduled in parallel. So it's a set of activities such that their requirement does not exceed the capacity, and also they are not linked by precedence constraints. Otherwise, they could not be scheduled in parallel, and their time window intersects also. So for example, here you have a list of activities that can be scheduled in parallel. You cannot restrict to the maximal fusible set, unfortunately, and there is an exponential number of them. But you can define a schedule as an assignment of a fusible subset to each time period. So if you suppose that you enumerate all the fusible subsets, you can remove the resource constraint and just say that you select one of these subsets at each time period. This is what Mingozzi et al. Did in 98. So I don't go into the detail, I don't have the time, but the YPT variables are variables that say that a given fusible set, capital P, is in process at time t. So you have to satisfy the task duration and link to the anxiety variables also. So if you would like to solve this, you have an exponential number of variables. So you have to do column generation to solve the linear relaxation, and branch and cut and price to solve the integer program. So time index formulation have limits. So these limits are the fact that first of all, I say that you have many equivalent formulations with the same linear relaxation, but it does not mean that in a solver, if you give the solver and you ask the solver to solve the problem in an integer way, you can have different results. For example, Bianco and Caramia show that the step formulation outperformed the others in terms of integral solving, and this is linked to the sparsity of the matrix for the step variables. And because modern solvers exploit the sparsity of the matrix, but it has nothing to do with the LP relaxation. Even weaker formulation in some, if you have no luck in your branch and bound, can give better integral solutions. And also, time index formulation cannot be used obviously for problems with a too large time horizon. So we need also compact or hybrid formulation. So I quickly describe the main ones. So the second family of formulation introduced keeps the continuous start time variables Si, but introduce a sequencing variable, binary variable Zij, which is equal to 1 if j is before I. Okay. So, for example, if we want to represent the solution below, we have to introduce the dashed arcs, which correspond to the Zij variables equal to 1. And if we apply a CPM methods on the resulting graph, we'll obtain the schedule below. So to be feasible, the set of all precedence constraint has to destroy all forbidden sets. That means that you must, this is the last constraint, you must define at least one precedence constraint for each forbidden set. But there is an exponential number of forbidden sets, right? So this is a non-tractable formulation. It was proposed in 93. So we can obtain a compact formulation by designing resource flow variables. Continuous variables saying the number of units transferred from an activity to another. So for example, here we have 2 units transferred from 1 to 2. We have 2 units transferred from 3 to 6 and 1 from 3 to 5. So we define resource flow union through the activities, and we can link the flow variables with the sequencing variables. If we have a positive flow, then we sequence the activities. So it's redundant because we do not need all the flows, but it's sufficient to destroy all forbidden sets. And so we can add flow variables to the model. And here you have the first constraint that links the Zij variables to the flow with a kind of big M constraint that prevents a sequencing if there is no flow between the task. So we have a compact formulation. but as I said, the relaxation is really poor. So some researchers try to deal with, to propose valid inequalities for this problem. And this formulation was originally designed for disjunctive problems like the job shop. So you have previous work by LAAS, Applegate, Cook, Dairel-Wolsey, etc., that defined a lot of valid inequalities for the disjunctive problems. And for example, I think the inequality of LAAS gives us this facet for the problem. So in this work with Sophie Demassé and Philippe Michelon in 2007-5, we tried to design such valid inequalities for the Rcpsp by using constraint propagation for lifting the inequalities. So, for example, with constraint propagation, you can define what is the minimum time distance between I and j if you schedule k before L. So you have 4 activities here. So you try to schedule k before L, and then you compute the minimal distance that you must have between I and j. So if you do that for the 3 possible relations, so L can be before k or in parallel of k, and then you can obtain a lifted distance inequality here. That gave at this time better bounds when you inserted it in the flow-based model. The last family of Milp formulation for resource-constrained sequencing scheduling problems is the event-based formulation that originate from the propositional variables of Keran, Dozer, Perez, and Lasser, notably for machine scheduling and flow shop problems. So you have a set of remarkable events, and an event will be the start of the end of an activity. And you introduce a continuous variable TE for each event, which is the time at which this event occurs. And you assign basically the start and the end times of the activities to the event. With A minus IE, if A minus IE is equal to 1, then the activity starts at event E, so its start time is equal to TE. And with A plus EIE, you assign the activity with the end time of the activity to the event. So SI plus PI is equal to E. So here you see, for example, the 10 events that are in the problem. So I don't detail the formulation, but you can express all the constraints easily with this set of variables. But we have, as you notice, we have an event per. We have a set of n² binary variables, one for the start and one for the end. We can do only with n variables by defining on-off event variables. So with the meaning that variable IE is equal to 1 if the execution interval of the task intersect the interval between TE and TE plus 1. Okay, so in fact, each activity such that AIE is equal to 1 can be assumed of length TE plus 1. It would mean to increase, in fact, for example, the duration of activity 6 until events 5, but it's not a problem for the Maxpan objective. So you can also have a formulation with this set of variables. And it was known to have a really poor LP relaxation. So rather recently, valid inequality were proposed to improve the LP relaxation. So with Margot Nataf, Tamaskis, and Marco Horvath in 2018, and also Pierre Lopez, we designed a non-preemption inequality with a polynomial separation algorithm. And then Tesh in 2020 improved all these valid inequalities and also proposed new event-based formulation, especially a kind of step 1 to have a sparse matrix that in practice obtain, let's say, competitive results with discrete time approaches. So to conclude on this part, before entering the last part of my talk about let's say the applications, a few hints of the Milp formulation for the Rcpsp. So if you have a small time horizons, so you should use a disaggregated time formulation because it has a better relaxation and it will be the most efficient. For large time horizons, you should switch to compact formulations. And one of the best is the one proposed by Alexander Tesch in 2020, which is an event-based formulation with a step behavior. With event-based formulation, it can be difficult to model some even linear objective functions. And also with continuous time formulation, non-linear, of course, objective cannot be modeled, whereas with the discrete time formulation, you can model non-linear objectives. You also have to look at the instance characteristics. Well, for example, you can look at the network complexity, which is linked to the density of the precedence graph, the resource strength, which is linked to the number of activities that can be scheduled in parallel in the resource. So for small resource strength, it's like a machine, and for large resource strength, you can schedule a lot of activities in parallel. And resource factor, which is linked to the number of resources required. So for example, if you have large high density, this will narrow the time window. So maybe you can still use, even for larger reason, the discrete time formulation. Also for we experience, but it has to be questioned now with the evolutions of the qualities of the valid inequalities from Tesch, that for disjunctive resources, maybe the flow-based formulation with the sequencing variables could be better than the event-based formulations. But anyhow, why using Milp for scheduling in practice? As I said, the CP can be better. So first of all, you can obtain good lower bounds with Milp. So either by solving the LP relaxations or by exact solution of some relaxation, for example, preemptive relaxation, or you aggregate the resource constraints. So we'll give a few examples of this. For particular cases also, sometimes Milp can do better than CP. This is the case generally when you have a lot of preemption, a lot of activities that can be interrupted and restarted. Also when you have sequence-dependent setup times, and also when you have some objectives and especially time-dependent ones. So in this particular cases, maybe Milp can be better than CP. And in any case, you can incorporate Milp inside hybrid methods, like in, for example, the logic-based Bender decomposition proposed by Hooker, or doing global constraints in CP, taking account of objective function values. So about lower bounds, it has been a lower bound based on Milp was the best one for a long time, actually, until at the end of the slide, you see that the best lower bounding method became the lazy close generation by Schutt et al. But how did this good lower bounding scheme work? Well, it was a destructive scheme. You try to fix a target make span, then you apply constraint propagation, and then you apply LP relaxation plus cuts. And if you prove that the M is infeasible, then you have a lower bound of M plus 1 and you can iterate. So with Sophie de Massé, we proposed this scheme with the discrete time formulation and the flow-based formulation plus cuts. But there were also a relaxation of the feasible set formulation called the weighted node packing combinatorial bound that was solved by iteration of constraint propagation and colon generation or Lagrangian relaxation. And this scheme with the use of the energetic reasoning constraint programming technique that gave additional cuts, the bound by Baptiste and de Massé was the best bound for the Rcpsp, at least for the PSPLE, for a long time, until it was beaten by lazy close generation. But recently, things are not over. So, for example, I think Moukrim, Hélène Toussaint, Alain Quillot proposed a branch and price to solve exactly the preemptive relaxation of the feasible subset formulation. So you relax non-preemption on the task. And sometimes you can beat lazy close generation with this on for lower bounding. Okay, so in red you see the improvement of this branch and price scheme over lazy close generation on the 60 activities instances from PSPLE. Another way of obtaining good lower bounds can be to solve exactly aggregations of the problem. For example, with Pierre-Antoine Morin, Damaskis, and Fritz Pixma and Alain Haït, we proposed a model where we divide the time horizon in buckets. It was also the principle of the paper by Riedler and al. And in fact, the buckets are much smaller than the size of the time horizon. And you see that the activities are scheduled inside the bucket, but the start time is somewhere inside the bucket. So you can schedule precisely the start time of the activity for the precedence constraint, but you use binary variables only on the time bucket to represent the resource constraint. And with this, recently, we managed to improve some bounds of the lazy close generation scheme on the pack instances from Carlier and Néron that are characterized by high resource strengths. It means that you can schedule a lot of activities in parallel. There is also, let's say, a struggle between Milp and lazy close generation on the multi-mode Rcpsp, when you can have several ways of scheduling the activities. So in 2017, Schnell et al. Proposed an extension of the lazy close generation technique, those hybrid CP-SAT method, to solve the multi-mode Rcpsp, and they obtained a new benchmark on this problem. But recently, Arrojo et al. In 2020 developed strong counting planes based on the technique on the discrete time formulation that I introduced, the cover inequalities, the lifted cover inequalities, and so on. And they followed this by branch and cut, and they improve, you see, an impressive number of open instances, but they have a rather high computational time for this. But as you see, it's not clear which method is the best. And I said also that for some particular constraints, then Milp can have better integer solutions than CP. So that was the case of the application I mentioned before of scheduling examinations of hazardous material. So you see here a problem where you have two technicians and a machine of capacity 2. And for example, activity A3 is A1, sorry, is preemptive. Okay, so you schedule activity A1 on technician 1, then activity A2, then you come back to activity A1, and then you switch technician here. So it's preemptive, and you can also switch from one technician to the other. You have also partially preemptive activities. For example, A3 is preempted on tech 1, but it occupies the machine. It cannot release the machine, so it's a bit of special constraints. And here we have a set of industrial instances characterized by different proportions of non-preemptive, partially preemptive, and preactive activities. And in the table below, we compare Milp and CP in terms of number of instances to solve to optimality and average time to optimality. And you see that CP beats the Milp for every instance set, except for the one where we have 80% of preemptive activities. So this is set A. We solve optimally 46 instances where CP, it was the last version of CP optimizer, solved only 29 for 10 minutes of computational time. So with preemption, actually, you can use Milp sometimes. And the last application is the runway sequencing problem with no maintenance activities. So I would like to show you that you can design sophisticated, let's say, hybrid methods that mix constraint propagation and Milp to obtain competitive algorithms. So first of all, what was the Milp formulation we used? Well, we used an extended formulation where, in fact, aircraft landing, takeoff, and snow removal separation were handled by click constraints. It means that we did not insert directly the sequence-dependent the separation times inside the model. We just enumerate the set of let's say activities that cannot be scheduled in parallel because of these separation constraints. So it's useful to get rid of the standard TSP matrix, let's say. And then, but we have an extended formulation, so we have to use colon generation colon and cut generation to solve the LP relaxation. But we did also a CP model. So actually, we use a CP model to reduce the variable domain and also to have a good start heuristic. And then we use this start solution to generate initial colons in our master problem. So we use CP both to reduce the time windows and for the discrete time formulation it's important, and also to have good colons at the beginning. And then we solve the LP relaxation with colon generation. And at the end, the relaxation was pretty good, and the upper bound was pretty good also. So instead of doing branch and price, we can use exhaustive enumeration of colons via the reduced cost constraints. And then we do branch and bound. So we tested this approach on instances from a big airport with, I say, the 3 runways, maybe 77 planes. And here you have the gap of CP. So CP could not solve to optimality any instances under the 10 minutes limit time, whereas our method, that is a hybrid method, CP, Milp, using colon generation, obtain much better results. So to conclude, I can try to give some perspectives. So I believe that there is still a lot of work to do with time aggregation, and notably using the dual feasible solution concept to improve the resource constraints. We can also have really interesting results when you have scheduling problems in which you have also continuous variable and possibly nonlinear objectives. But to come back to aggregation of time and resource, there is a very interesting method that was developed, but more in the routing and network design domain, where you define a partial time expanded network and you discover dynamically which time points are interesting to be generated. So it could be interesting to see how DDD, dynamic discretization discovery, could be applied to some scheduling problems. Also, pre-processing is really important for Milp. So for machine scheduling problem, there have been a lot of impressive improvement by reduction of the number of variables. It has not been really done for the Rcpsp, and also we are not able still to use branch and price, or branch and cut and price, sorry, for non-preemptive feasible set formulation. So sorry for the orthography here, but Pierre Fouillou and his co-authors designed recently a branch and cut and price algorithm for the preemptive feasible set formulation. So we could try to do that for non-preemptive formulation, because this is the problem we have to solve. But for now, nobody managed to have a good results with this kind of methods. And also, there are other models for extended formulation. We could use a chain decomposition. Feasible set decomposition are, let's say, vertical decomposition. You enumerate the set of activities that can be scheduled in parallel. But for example, Van den Akker et al. Design extended formulations for parallel machine problems where you can enumerate the chains. It means activities that have to be scheduled in chains. So for the Rcpsp, it could be interesting to test this. And I think a really promising way is to understand the link between the closed learning and the cutting planes in Milp algorithms, to design hybrid SAT, CP, and Milp approaches. And there are already ongoing works in this area. And of course, we have also to consider uncertainty, and I did not mention this in the slide. I forgot, but mathematical programming can be also of help when you have to solve multi-stage adjustable stochastic or robust scheduling problems. So here also hybrid methods could be of great help. So I thank you very much for your attention. So here are my co-authors. I think of all the papers, giving you the references for the record. Thank you very much.
Okay, thank you, Christian. And now I have let you to unmute yourself. So if anybody wants to ask a question, you're welcome. So if nobody is coming, let me just ask Christian, so many smart people working on one problem, so to conclude, and still we have many open instances. So what's the core of that? So if you look, for example, on TSP, they are marvelously going up and up in the last decades and solving larger and larger problems. Rcpsp seems not to be so far from there, but it probably is. So what is really the difficulty there?
Well, it's a difficult question also.
Yeah.
But I don't know. The fact is that Rcpsp maybe is not as homogeneous. Maybe people from TSP will not like that, but not as homogeneous as the TSP. It means that Rcpsp encompasses a lot of different problems. If you take a resources of capacity 1, you obtain disjunctive problems, for example, and they are very well solved. So we try to extend the methods from disjunctive approaches to solve the Rcpsp, but it's a totally different problem when you have resources with non-unitary capacities. Also, the structure of the precedence graph can make the problem really different. So I think that maybe the fact that, yes, you can have problems with less than 40 activities that are not solved today. And this problem, maybe the fact is that it's because we try to solve the problem in its generality. And maybe it's too difficult. We should maybe consider the different categories of problems. Maybe you could do learning to see machine learning to study in which category we are when we are solving a particular instance to switch to the good method. That's it's a good question.
Okay. So any question? So there is some questions in. So I can read it. The question is by Minyu Chui, and the question: may I ask a question here? Sorry, I can't use microphone. What is the size of solved problems? Like around how many variables and constraints?
Yes. Well, I don't have example of the size of the Milp, but as you see, with 2 activities, it was already 11 binary variables, for example, for small discrete time. So you can have hundreds of binary variables. So it starts to be very difficult.
All right. So binary variables, number of them is less than 1,000, definitely, right?
I think, well, for the 60 activities instances,
it's more.
It's less than 1,000, but it's still not reachable by the current Milp approaches.
Okay.
But I wouldn't. I have to check. I'm sorry. I did not prepare this one.
and
if someone has the answer, he can maybe.
Many people are expressing their thanks to very nice survey that you did. And Jan Karel is mentioning that this problem is harder than TSP, especially if you consider metric TSP. Definitely, it is a harder problem. We have also several resources and comparing to TSP, right? Okay, so if there is no other question, there is one more message.
Cumulative constraints. I see a question. When I refer to CP, it's constraint programming, actually. So
yeah. Constraint programming. I understand. Yeah.
So the set of techniques that are embedded in what we call constraint programming. It's a technique that uses a logic model for solving a problem and separates the constraint propagation that make inference on the constraints and the solving with tree search. So we have, for example, for scheduling the CP optimizer solver, and then constraint programming is really competitive for scheduling problem. And
but I think that
cumulative constraint, it's just the name of the kind of constraints we have on the Rcpsp.
I think the CP optimizer was really fine-tuned to solve well Rcpsp problem, right? So it's not that surprising that it's doing really well. If you would have opportunity to change the inside of ILP solver, probably you would be in better position. So there's another question, Eduardo Moreno.
They are in the general case, they are inapproximability results. For particular cases, of course, there are approximation algorithms, but in general, it's inapproximability results. And I'm not a specialist of this field at all, but
okay, so that was answer to a question by Eduardo. Okay. Okay, so another question, if you can read it and respond.
Yeah, for an instance of more than 2,000 tasks to be scheduled with machine capacity more than one, so this is supposed to be a big problem. If yes, which method do you think will be suitable? Well, when you start to have more than 1,000 tasks, I think that you can still handle this with CP. Of course, the search tree will not finish. You will not have the optimal solution, but CP, some CP solver will give you maybe a good solution to let them enough time. But in this case, you can also resort, of course, to meta heuristics. There are a lot of them. So I would say either a CP solver or meta heuristics in this case.
Okay, you may maybe take a look at these benchmarks and to see on the largest benchmarks which of them have been successfully solved. But definitely hyperheuristics and meta-heuristics are among them, right? Another question by Christian Weiss.
Yes, about sequence-dependent setup times. Yes, actually, for now, well, when you think about sequence-dependent setup times, it's equivalent to a distance matrix in the TSP or VRP problems. To my knowledge, for the present time, these problems are better handled by mathematical programming techniques than CP, except maybe for special case with tight time windows. So you can have the standard TSP or VRP path formulations, for example, to solve the problem. In the problem I presented with the separation matrix, we use the click inequalities. That is, we enumerated the set of activities that are incompatible with respect to the separation. Well, for scheduling, I would advise. The question is, which CP solver do you use for benchmarking? So for scheduling, I would advise to use either CP optimizer from IBM, which is a commercial solver, or the Chuft solver, which is the one that is benchmarked in the slide, but it was the version of lazy close generation in 2013. So maybe now the Chuft has better solution. But what people say in the field, I think that Chuft and CP optimizer are the best one. But I think that also the solver from Google now can have good results also in CP.
The one which is part of OR tools, right?
Yes, but I don't remember the name.
Okay. So thank you, Christian. It was exhaustive. One more question. So, question. Periodic activities.
Yeah, periodic. Yes. There is the cyclic resource constraint project scheduling. So I personally worked on an application on this. It was on parallel processor architecture. We had a periodic Rcpsp because, in fact, you have to schedule loops of 1 million iterations, for example. So you have to do 1 million times the same stuff. So it's like a cyclic problem. And so in this case, in fact, Milp competes with CP because in the case I considered, it was unit time activities. Because in processor everything is synchronized with the clock. Okay, so you have unit time tasks to perform, and there is a constraint programming approach by I think Michela, Milano, and others, and also we designed a Milp that was pretty competitive in this case. But I'm not aware of work on cyclic scheduling or periodic scheduling with non-unit activities, but it's a good research perspective.
Okay, so thank you, Christian. I think there might be many other questions, but we are short in time. Typically, our talks are much shorter, but I think it was worth of having it. Thank you very much. Thank you to everybody. And just let me remind what will be the next talk in 2 weeks. We will have Pascal van Henterik speaking about constraint programming for scheduling. So you have done a really nice introduction to his talk. So I hope to hear you and see you here in 2 weeks. And we will speak about constraint programming. And Pascal Henterik is an expert in this field, so I'm pretty sure that it will be a very successful talk. Thank you very much, and stay with us. Bye-bye.
Thank you.